So in this video, we'll look at some code that will help us analyze completely randomized design. And in particular, we'll implement some of the contrast material that we learned about in the last lesson. So let's consider this data set of the measurement of plant heights for 4 different fertilizer treatments. So this is similar to a data set that we looked at previously, but this data set also contains a blocking factor, which we will explore a little bit in the early parts of this question and then ignore until we learn about block designs in the next lesson. So first, let's just load the data, save the treatment variable as a factor, and print summaries of the variables, so things that we've done plenty of times before. I'm doing that here with the tidyverse. This mutate function down here allows you to save the treatment and the block as factors. And in addition to doing that, I also want to think about a few different questions from earlier lessons, like, does this study involve replication? Is it a full factorial design? And are there repeated measurements? So in order to answer those questions, we'll have to look down here at the data. And as a side note, I encourage you to pause the video and answer these questions on your own, and then resume the video and see what the answers are. So I think that'll be good practice for an exam, for example. All right, so here's a layout of the data, and we can notice that if we think about treatment and block as factors and look at the way that these things match up, so treatment has 4 levels, 0, 1, 2, and 3, and block has 6 levels, 1 through 6. We should notice that, for example, the combination 0, 1, so treatment 0, block 1, only occurs once, and that's true actually for every combination. So if we're considering both factors, treatments and blocks, then no, the study does not involve replication because there are not repeated observations under the same combination of factor levels. So we don't have replication. Now, if we were to ignore the blocking factor, right, if we didn't measure these blocks, which is really positions on a bench in a greenhouse, then we could say that we do have replication because we wouldn't have combinations of treatments. We would just have one treatment and we would have repeated measurements. So is this a full factorial design? Well, yeah, it is a full factorial design because it includes all possible combinations of the levels of the 2 factors. And so that you can see just by going through and seeing that, you match up. You have 0, 1 through 0, 6, and then you shift to 1, so 1, 1 through 1, 6, etc. So you do have a full factorial design. So the last question, are there repeated measures? In this case, there aren't repeated measures. So each plant is measured once for each level of the factor combinations. All right, so now let's ignore the block variable. And in doing that, we'll assume that all the units are the same with respect to other variables that impact plant height, for example, sunlight. And so we're not going to take into account like the position that they occupy on this bench in the greenhouse, which could differ with respect to sunlight. We're going to ignore that for now. And we'll also assume that treatments were randomly assigned to plants, so different fertilizers get randomly assigned. And in that case, we'll make an assumption that we have a completely randomized design. All right, so let's analyze this completely randomized design experiment and answer the following research questions. So 1, are there differences among treatment groups? And we should know how to answer that with a particular hypothesis test. And 2, is there a difference between level 1 of the treatment and level 3 of the treatment? And just as a reminder, the number scheme for the treatment was 0 through 3, so we're actually looking at sort of the level 1 as like the second place in the factor levels. And that second question we're going to answer using contrast. So in general, I think it's a good idea to use visualizations and sort of more informal analyses, but also to conduct the formal analysis that's appropriate for a completely randomized design, which in our case is a one-way ANOVA, now that we're ignoring the block variable. So this code here, you've seen plenty of times before. It constructs violin plots that allow us to, visualize differences. And so that plot is here. I'll zoom out just a little bit. So here we can see treatment along the horizontal axis, plant height along the vertical axis, and we see that the control, the zero level of the treatment, is lower on average than the other treatments, which are the fertilizers. But we do see that there are some differences between, say, treatment 1, 2, and 3. And we should also notice, we're going to compare treatment level 1 to treatment level 3, and notice that those two look pretty similar. And so, we're going to look at a formal test to see whether the test says that there's a statistically significant difference between the two. All right, so the formal way to analyze these data are one-way ANOVA, and we've learned that we can conduct a one-way ANOVA as long as we have our treatment stored as a factor. So if this is stored as a factor, then we can just perform a linear regression with the continuous response tilde the treatment as the formula. And if we look at the summary, we will see a bunch of important information. One piece of information down here, this p-value for the full f-test, answers the first research question, which remember was, are there any differences among groups comparing from the control to the treatments? And this p-value is very small, so it says we should reject the null hypothesis that there are no differences and conclude that there are some differences. Right? So you should be able to tell me how to interpret each one of these estimates. And for example, if you wanted the mean value of the response in the first level of the treatment, so not 0 but 1, you would add 21 and 7.6 to get that mean. So 7.6 is the difference between the baseline control, the 0, and the first level. Now I think it's worth mentioning that these least squares estimates that you get from linear regression are equivalent to conditional means, say y1 bar, y2 bar, and y3 bar, that you would get from just taking the mean of the response where you set the treatment equal to 0, 1, 2, or 3. So in particular, here I've set the treatment to the 0, the control group, and I've taken the mean of y, and then I've subtracted off the intercept term in the model above, and that gives me effectively 0. And that tells me that those two numbers are the same. So that's true for all of the means. So if you took the mean of y, fixing the treatment at the level labeled 2, and then you subtracted off the intercept term plus the coefficient associated with level 2, so this 4.86 or so, you also get 0. All right, so I think that's a good equivalence to draw. The nice thing about the regression setup is that it allows us to perform some formal tests. So down here, just a summary. The full f-test helps us decide whether there are differences across groups. Here are the estimates of those differences. And now we come to the question of how could we estimate the difference between treatment 1 and treatment 3, and then how could we test whether the difference is statistically significant. So that comes from contrasts, and we learned about contrasts in the last lesson. I've repeated some of the definitions here just so that you can see them, and I've also done some derivations for this problem. So just as a quick recap, contrasts are linear combinations of parameters and constants, and we just need the condition that the sum of the constants is equal to 0. And really what they help us do is understand how to evaluate certain hypotheses that make comparisons beyond just the full f-test. So for example, suppose we want to test our second research hypothesis, the comparison of treatment 1 and treatment 3. So I've written the hypotheses out here, and just as we did in the last lesson, we noticed that we can understand the null hypothesis in terms of a contrast gamma. And on the left side of the expression, we see how we can actually write down the coefficients so that this thing is in fact a contrast. And then I do here what I did in the last lesson, which is just go through the estimation procedure, calculate the expected value and the variance so that we can come up with a test statistic. So let's now implement that in R. So in R, I write down my contrast, so the constants that go into the contrast. And then I just store, just for simplicity of coding, I store the coefficients of the completely randomized design above in a variable b. N is the total number of units. And I compute a few things, right? I compute the residual sum of squares because I need that to estimate sigma. And then I actually estimate sigma using sigma hat, so that's the square root of the residual sum of squares divided by its degrees of freedom. And here I've written down gamma hat. I've written it down in a slightly convoluted way. I could simplify this a bit, but just to show you where it comes from, right? Up here, I've substituted in y1 bar minus y3 bar with the equivalent statement in terms of regression estimates. So if you're not convinced of this, go back up and convince yourself that this is the right set of regression estimates that really estimates this difference in means. And then of course you can simplify, the intercept term goes away. So that estimate turns out to be negative 0.6. And notice what you're doing. You're subtracting the third level from the first level. And so that tells you that the third level is larger, right? Whether it's statistically significantly larger is the question that we're attempting to estimate. All right, from there we can actually calculate t. So we take gamma hat in its simplified form in the numerator and divide by the standard error in the denominator. So notice this 6 here is the number of experimental units within the first level and the third level. Ooh, all of these n's should have 3's instead of 2's. I'll fix that in a minute. But in each level there are 6 experimental units. And so we get a t. The t statistic is small in magnitude, and so that means the p-value that we calculate here will be large. And so that tells us that we'll fail to reject the null hypothesis, which means that we don't have evidence to suggest that the mean plant height for treatment 1 is different from the mean plant height under treatment 3. So if we go back up and look at the plot that we had, notice treatment 1 mean, treatment 3 mean, those are pretty close, and so we don't have evidence to suggest that those are very different. All right, so the last thing that I wanted to mention was that, well, after all that work, there is a built-in R function that would do this for you. It's in the molt-comp library, so you'd have to download that library, load the library, and then this glht function will allow you to to perform the same test with a contrast from above. So the summary gives you this table down here, and this table gives you the estimate that we just found. It tells you the standard error explicitly, the t-value, and the p-value. All right, actually one more thing that we should mention is the relationship between the CRD and causal effects. And so I want us to think back to the 3 important conditions for establishing causality from our Intro to Experimental Design video. And let's think about how this experiment might help us satisfy some of those conditions. So a CRD can help with each of the components. Remember, there were 3 that we talked about: empirical association, a temporal relationship, and non-spuriousness. So for empirical association, really that's what ANOVA is all about, right? The mathematics of ANOVA allows us to detect empirical association among variables. And so, the math itself allows us to find association. And if we have these 2 other conditions met, then which the experimental design helps us achieve, then we can say something about causality. So what about the correct temporal relationship? Well, we know in the experiment that we applied the treatment and then we observe the response. And so in that case, we know that the predictor comes before the response in time. And so the CRD allows us to know something about temporal structure based on that setup. Now, what about non-spuriousness? Well, we have to be reasonably sure that the experimental units are homogeneous with respect to the response variable. For example, there's no lurking nuisance variable like sunlight that's having some systematic effect. And so if we assign the treatments randomly and we have homogeneity, then variables other than the treatment variable can reasonably be ruled out as a causal explanation. So basically, we're ruling out other possible explanations and saying that the treatment is really the only one that's left. And that's only really true under these assumptions of homogeneity and randomly assigned treatments. And we know with this data set that we've recorded a blocking variable, and it's quite possible that that blocking variable is systematic, like has a systematic relationship with the response. And so in the next lesson, we'll look at how to use that blocking variable if we believe that it is associated with the response.